Hello, welcome to the videos about spectroscopy. So these are going to be lectures over multiple videos, and we are going to focus on different techniques here. We will be covering molecular spectroscopy such as ultraviolet, visible spectroscopy, infrared spectroscopy, fluorescence, as well as atomic spectroscopies like atomic absorption and atomic emission spectroscopy. So before we get started on the content, I'd like to refer to you that the several materials among these lectures are coming from different sources, from two fundamental books in basic analytical chemistry by Professor Skog and Christian, as well as a strong influence has been from my own analytical chemistry teachers, namely Professor Iboleto, whose several slides I have gotten inspiration from his materials. So I'd like to thank these sources for being inspirational for this lecture. So before we start in going into specific spectroscopy types, we can think of what kind of spectroscopies generally exist. And spectroscopies can be divided and are divided actually simultaneously depending on the types of interactions that we are measuring with our spectroscopy or depending on the type of the analyte. And when we talk about the interaction type, then we talk about either radiation spectroscopies, which are all of the spectroscopy types that we are going to view on the next few days over the coming lectures. And on the other side is located mass spectrometry, which in English is not called spectroscopy, but spectrometry. And this comes from the fact that we are measuring the interaction of the charged species with the magnetic field. Also, essentially, we are measuring mass of ions in gas phase. While in radiation spectroscopy, we are measuring the interaction between the light, the radiation, and the material that we are studying. And as said before, we can also divide these spectroscopies depending on if we are dealing with atoms or we are dealing with molecules. And this is applicable both for the radiation spectroscopy. We can have atomic radiation spectroscopy and molecular radiation spectroscopy, but also for mass spectrometry. Both we can deal with atoms in mass spec as well as with molecules. And with molecules, we have to think very broadly here. This is not only neutral molecules, but these can also be metal complexes with neutral molecules or with ionic molecules, as well as ions here. So molecular ions also belong to molecular spectroscopy. So when we start digging into radiation spectroscopy, then first it's good to look at what kinds of radiation we even might have to be used in the spectroscopies. And actually the range is really, really wide. And here we focus only to some parts of it. So the whole range of the spectroscopy radiation that can be used in spectroscopy is very wide. When we talk about the range, then the energies lie from 10 in the power of 7 to 10 in the power of 21 hertz for the quanti that we can use in the radiation spectroscopies. And the most energetic spectroscopies are gamma spectroscopies, which are followed by X-ray spectroscopies. And after this come all kinds of visible and ultraviolet light related spectroscopy types, So here belong, for example, UV-vis absorbance spectroscopy, as well as fluorescence, as well as atomic absorption and atomic emission spectroscopy that we are studying here. And so when we look at the energies of the radiation that can be used in spectroscopy, then this energy range of the quanti that can be used is very wide. The highest energy quanti can have energy of 10 in the power of 21 hertz, while the least energetic ones can be in the 10 in the power of 7 hertz. And the most energetic quanti are used in a gamma spectroscopy, as well as in X-ray spectroscopy, which is of great use in determination of metals from different solid media, for example. And probably you have also experienced X-ray spectroscopy yourself at the doctors. But in here, next lectures, we will be focusing on slightly less energetic spectroscopy, so ultraviolet absorption spectroscopy and fluorescence spectroscopy, as well as atomic absorption and emission spectroscopy. And these spectroscopies deal with infraviolet as well as visible light. And these spectroscopies make use of light for which the wavelength, usually we express this wavelength range in nanometers, is from in the range of a few hundred nanometers. So usually we do the measurements above 190 nanometers and up to 750 nanometers. Slightly less energetic yet is infrared spectroscopy, and infrared spectroscopy is having a higher wavelength, so above 1000 nanometers. And even less energetic are microwaves, which observe the rotations of the molecules. And radio spectroscopies, such as nuclear magnetic resonance spectroscopy, that will be viewed also later in this course, is dealing with the least energetic radiation and the interaction of the spin and the spin of the molecules and the radiation. So this is something that will be viewed later. But next, in the next lectures, we are focusing here in the middle of this energy diagram on the ultraviolet fluorescence infrared spectroscopy. So when we think about, when we for a second go through these different spectroscopy types, then the X-ray spectroscopy is dealing with atoms, so it can be very nicely used for determination of different metal atoms. And this is due to the fact that X-ray radiation is interacting with the inner shell electrons of the atoms. Ultraviolet spectroscopy, visible spectroscopy, fluorescence, as well as atomic spectroscopies are dealing with bonding electrons. So the electron excitement niveaus are being used to generate these spectra in these spectroscopies. In near-infrared spectroscopy, we are dealing with the vibrational energy niveaus of the compounds. So we are studying how the molecules vibrate in the media. And the same both for the near-infrared as well as infrared spectroscopy. And in radio spectroscopy, we deal with the spins of the nuclei. Two important definitions for the lectures to come are excitation and relaxation. So excitation is the process where the molecules or atoms are gaining energy, and therefore the electrons of these molecules or atoms are going to a higher energy level or higher energy level. So this energy can either come by absorbing energy from the surrounding media, by, for example, colliding with particles. So this is highly related to the temperature of the medium. So the higher the temperature, the more the molecules in our media are colliding, molecules or atoms, and therefore the more likely becomes the excitation of the compound. Another important part is absorbing a quanti of radiation. So this is what we use in absorption spectroscopies. So the molecule that we are studying is hit by a quanti of a suitable energy, which can be then absorbed, and the molecule can go to a higher energy level. In comparison to excitation, relaxation is the way how the molecule is transferring back from the excited state to the ground state. And this can again be either non-radiative or radiative relaxation. The non-radiative relaxation is happening if the molecule is just colliding with other molecules in the media or atoms, and therefore this energy is lost essentially as heat by just the collisions. Or another possibility is a radiative relaxation. So the energy is emitted as a light, so as a quanti. So, and this is especially important in fluorescence spectroscopy as well as in atomic emission spectroscopy. And when we look these processes all on a small energy diagram of a molecule, then this hopefully becomes a bit clearer. So here on the y-axis, we have the energy of the molecule, so the energy states of the molecule. So the higher up the energy state is, the more energy this state has, and more energy is also needed to bring the molecule up to this state. At room temperature, molecules are at the ground state, and we can see here that there is one long line which denotes us the electronic state. But then we also see slightly shorter lines which show us the vibrational energy states. So this means that the molecules can become more intensive, can start more intensively vibrating, and therefore gaining vibrational excitation, even if the electronic excitation is still in the ground state. And between these electronic excitation states, we also see vibrational states. So it's not, we also, in addition to this vibrational states, we also see here in between rotational excitation states. And this is the rotation of the bonds. So we have three different niveaus or energy states here related to the electrons of the molecule, related to the vibration of the bonds in the molecule, and related to the rotation of the bonds in the molecule. And due to the fact that there are so many vibrational energy niveaus for molecules now, then the spectra become almost continuum spectra. And we'll see that from the spectra in ultraviolet spectroscopy very clearly. So this means that they are almost continuous energy levels here. They're not absolutely continuous, but they are very, very close by to each other. And most molecules are in the ground state at the room temperature. And what can happen is that when we pose light to our sample, then this light can be absorbed by the molecules when the wavelength of the light matches with the energy required for the molecule to be excited to a specific energy level. And for example, here we can see that this tiny example has two electron excited levels, S1 and S2. And within these electron excited levels, again, we see both the vibrational as well as the rotational excited levels as well. So both in the ground state, the molecule can have multiple vibrational excitation levels, as well as at the electron excited levels. This can happen. And usually when the molecule absorbs light, then the compound is brought to some electronic excited level, as well as it gains some rotational and vibrational excitation. And what happens thereafter is that the rotation and vibrational excitation is usually lost by collisions with other particles in the media. So the molecule very quickly comes down to the ground level from the rotational and vibrational point of view. And it can also come down from the electron excited state to the ground state again by just colliding with other molecules, but it can also come back to the ground state by emitting light. And this is what we observe in fluorescence. So absorbing the light is something that we study in ultraviolet visible spectroscopy, and emitting the light we observe in the fluorescence spectroscopy. We can also study the vibration and rotational levels of the compound directly by IR spectroscopy. So in IR, what we do is that we give less intensive light, we pose less intensive light, so infrared light, on our molecules, and as a result, the molecules can become excited rotationally or vibrationally, and we can measure how much light has been absorbed by the molecules to bring about this rotational and vibrational excitation